This is our presentation on MiningMath, explaining how the first and only single-step mining optimization engine works and how it compares with other technologies on the market, as well as our differentials. First, we'll go through the problem MiningMath is trying to solve, then we'll make a technical comparison between technologies, then we'll go through the interface and then the results. And by the end of this presentation, I'll show you how it can impact your project and boost your investments. How global is your optimization? When you look at the problem too closely, you can't see the next steps. One decision limits the next. You don't know what you might be missing. But what if we had access to a much wider range of solutions? Analyze the project with different eyes? Found different, more profitable sequences? Let's see. To bring you some points from best practices on the market, let's call them stepwise technologies. As the name implies, they have steps for solving the mining problem. First, you need to generate your nested pits, then add the geometries to define the pushbacks, and only then insert the rest of the variables to generate the schedule. You can also generate the short-term planning if you wish. However, all these steps are limited because one step limits the next decision and the next and the next, and they always generate similar solutions, no matter how many iterations are made. After all, everything has the same root, the nested pits. With these approaches, we have some situations, such as gap problem. The green line is the production we want to maintain, but they deliver production gaps and spikes, which is not feasible in real life. You need to predefine the cutoff grade. They only deliver a single sequence based on revenue factors. The sequence will always be the same. They deliver the sequence bench by bench, i.e. they always mine an entire bench before moving on to the next one. They can also deliver partial benches, in the Z direction, by cutting the blocks in half. And they deliver approximations of the general slope angles, since they use the block precedence method, and this method is associated with some geotechnical errors that prevent the angles from being precise. All these points lead us to some questions. What if your nested pits do not lead to feasible production plans? What if your pushbacks do not account for your blending needs? What if your short-term planning does not fit the long-term view? What if other geometric conditions could be tested for a better NPV? What if your cutoffs and sequence incur higher mining rates and stocks? It is possible to go beyond the limitations of the stepwise methodology. And now I'm going to show you how MiningMath solves these points. Firstly, you can see from the diagram that MiningMath doesn't work step by step. So you have your block models, you enter all your variables, and depending on which one you enter, you can generate different scenarios with different results for analysis, straight from the block model. And with these features, you can identify your bottlenecks before going into detailed planning. Check how each constraint interacts with each other. Test how each premise impacts the economics. Search for realistic lower risk and higher potential scenarios. Reveal hundreds of unseen distinctive solutions. Now we have the same points compared to the step-by-step technology, with the detail that all of this, which we will see below, can be done with the free version of MiningMath. Unlike what we've seen, MiningMath manages to deliver stable production. It doesn't need a predefined cutoff grade, since the decision as to whether the block is or waste is made based on the economic value of the blocks and not on the cutoff grade. Unlike stepwise, we have the ability to deliver multiple different scenarios, since every small change in any variable can completely change the sequence of the mine. There is no bench-by-bench extraction, but our math optimization instead. We don't have the problem of partial benches, since the entire blocks are always mined. And we are able to deliver more precise angles, since we don't work with the block precedence method, but with surfaces, eliminating geotechnical errors. Now I'll show you what else you can do with the full version. The first thing is that you can not only control the movement of ore, but also the waste, so you have absolute control over the total movement of the mine. We also work with a multi-destination policy, so if you have more than one process, or more than one product, we can deal with it. And with a stockpile for each process. Next, we have what we call average or sum variables, which can be any restrictions that are based on the average or sum of the blocks. The most commonly used are blending, type of material, hours of equipment worked, CO2 emissions, among others. There are also surface restrictions, of which there are two, forcing and restricting. Force mining is used to deplete the material in the entire area within a specific time period. This function is responsible for ensuring that MiningMath achieves at least the inserted surface, meaning that all the material within its boundaries must be extracted, whether it is or waste. Finally, there are the geometric constraints, which are more operational variables. There are 4 available: vertical rate of advance, bottom width, mining width, and mining length. Mining length is a variable you don't see very often on the market, and we've implemented it to be used in conjunction with mining width. This is the homepage of our website. Here you can download the free version of MiningMath with a 60-day free license if you've never used it before. And here we have our knowledge base, where you can find all our content, from tutorials to in-depth descriptions of our algorithm, advanced techniques, and articles about our technology. There's also the forum where our community can help with any questions. And if you still couldn't find your answer, we also have our bot with instant support 24 hours a day. All this to provide maximum support for our users. The results from MiningMath consist of Excel charts and tables, generated automatically. Tables also available inside MiningMath. Sequence development files with the information about mined blocks, period mined, period processed, destination, as well as the original properties, named mineblocks.csv or allblocks.csv. Surface files in a grid of points for each period of the life of mine, named surface. As we have these in CSV, it's possible to integrate with other softwares. Here we have what we call integrated workflow, showing that, if the user wishes, it is possible to reach intermediate stages of modern technologies using MiningMath, adding restrictions according to the type of result you want. However, with MiningMath you do this directly from the block model, having a much wider range of solutions, revealing more possibilities and refining during this process with the help of decision trees. This is a practical example of decision trees. We have the base scenario and test the variation of some parameters, such as the variation in the price of copper. Thus, it is possible to assess how each change impacts NPV, production, mine sequencing, and the entire project. This allows access to hundreds of optimized scenarios to support strategic decisions. That's why it's important to generate decision trees to identify bottlenecks. Here we have more than 2,000 scenarios analyzed, including several variables alone, and an overall variable with random combinations of variables. This shows how important it is for you to know all your variables and how the inclusion of each one has an impact on the final result of your project, as well as how one influences the other. And all these benefits and differences have already been and are being taken advantage of by various companies around the world. Be part of it too. What are you saying? Let's start this journey together.